In the second tutorial for tsunamis, we're going to look at the issue of tsunami height. That is, how high is the tsunami when it reaches land? And that's a problem because the tsunamis grow when they reach land. Their name actually is related to that. Tsunami means harbor wave because it's something that wasn't seen until you're in the harbor. Out in the open ocean, it's typically less than a meter, maybe a meter high, and it's got a wavelength of hundreds of kilometers, so it's about as flat as something can be. But the height does grow when you get into the shallow water, and we see that in the devastation that occurs. So what we want to do is, using the physics of tsunami waves, calculate how high the tsunami will be when it reaches land. The thing we know is we do know that the wave at the buoy is something like a meter, meter and a half high in positive amplitude. And so we can use that because it ends up that the tsunami height can be scaled by this relationship. In fact, the formula as given to you in the handouts says that the height of the tsunami squared at one location relative to its height squared at another location. So H1 would be at location 1, H2 would be location 2. In both cases, they're squared. They're actually inversely related to the speed at that point. When the tsunami wave slows down, the wave gets bigger. And so this is scaled by the ratio between the speeds at those two locations, and those are simply going to be the water depth, the square root of the water depth at those locations. So in this case, we're in pretty good shape. We can take this formula and rearrange it, and we can say then that the height of the wave at location 2 squared will equal the height of the wave at location 1 squared times the ratio of GD1 over the GD2, the square roots of those. And so this formulation we can use so we can calculate this, because we know, for example, the height of the tsunami at the buoy, we know the water depth at the buoy, and we can then put in different water depths at different locations to figure out what then the height would be at this location. Remember, we've got squares and square roots here, so be careful with that. And so we know the water depth at the buoy, something like 5,000 meters, so we might say that D1 is equal to something like 5,000 meters. But then that raises the question, what should the water depth near the coast be? Because obviously at the shoreline, the water depth goes to 0, and at some distance out, it's going to be deeper. And so this is actually a problem. And so what we tend to think about is what would be the typical water depth, say within a few hundred meters of the coastline, because that's going to be essentially the distance over which the wave finally grows. And so you might look at something and think about, if you've ever been to the beach or profiles along other beaches, what is the water depth in the nearby areas? And it is actually the variation in that can affect the actual height. In fact, if you look at the data that's given in the handout from the actual data recorded after the tsunami, we see that the height varies over a large amount. Some of this variability is actually due to the nature of the earthquake rupture, but a lot of the variability in any one location is a consequence of subtle differences in the near coast shape, either the shape of the harbor or the actual shape of the water. We can't deal with those things with the type data we have, but we can still get an estimate of what the near shore, so we want this to be near shore water depth is like, and that will then tell us something about the height of the tsunami at that point. What you then might want to think about as you do this assignment is, based on that, and then looking at the actual pattern of tsunami heights up and down the coast, think about what might be the cause for these large variations, and in particular, what might cause the really high values. Because when we apply this to other places, next week we'll be worrying about tsunami inundation along the Oregon coast. It's important to think about, we can do our calculations, but then we have to think about how much we need to amplify those to account for the natural variability that could occur. So both of these things, both the velocity and the height, are well represented by the calculations, but we have to remember also that the calculations are for the simple geometries, and the real coastal environment may be more complicated than that. So that ends the second part of this, and you should be in a position now to do the calculations that we're asking of you for this week.